Hello students, Mr. Courtney here. In this video, I'm continuing with gas laws and I'm going to be discussing effusion and gas stoichiometry. So we'll define and discuss effusion in terms of, and we'll discuss Graham's law also. We'll calculate the molecular weight of an unknown gas and perform gas stoichiometry problems. So we've already discussed the assumptions of the kinetic molecular theory. We stated that the gases are made up of tiny particles that are far apart relative to their size, so the volume of the particles are negligible. These particles are in constant, rapid, random motion. There are no attractive or repulsive forces between these particles under normal conditions of temperature and pressure. And that collisions between the gas particles and between the particles and the walls of the container are elastic collisions, so no energy is lost. And that all gases at the same temperature have the same average kinetic energy. And that means that energy is proportional to the absolute temperature. We've also looked at equations that fit the behavior of gases that have been observed experimentally as they approach ideal behavior. So take, for example, someone opens ammonia at the front of the room or sprays a sweet smelling perfume at the front of the room. Now it takes a while before everyone can smell the perfume because it has to mix with the air. The rate of mixing is the rate of diffusion. And we also have a term called effusion, which is the passage of the gas molecules in a closed container through tiny openings in the container. So the passage of these gas molecules through these small pores into the vacuum, into an evacuated chamber. So how long does that take, and what controls the rate of movement? So that's what we're going to look at when we talk about effusion here. So Graham's law. Graham's law states that the rate of effusion of a gas is inversely proportional to the square root of its molar mass. So the rate of effusion measures the speed at which the gas is transferred into the chamber. So this is the equation we'll use. The rate of effusion of A divided by the rate of effusion of B is equal to the square root of the molar mass of B divided by the square root of the molar mass of A. So rate is 1 over time, and M represents our molar mass. Now the law also holds true for diffusion, which we talked about a bit before. And we said diffusion is the mixing of gases by a random molecular motion. So we look at some examples of how we can utilize this Graham's law to determine molar mass and also compare rates of effusion. So at the same temperature, light molecules will diffuse faster than heavier molecules. So here we see an example of this. Helium, which is lighter than neon, is going to diffuse. All right, we'll get to that space, that hole, much quicker than the neon molecule. And we can also see when we mix gases. So here we have ammonia and hydrochloric acid or hydrogen chloride being mixed. So we have cotton soaked in hydrochloric acid and cotton soaked in ammonia. And these liquids will produce vapors which will travel the length of the tube. The point where these two gases meet and mix is where we're going to form that white ring of ammonium chloride. But notice the distance traveled by ammonia compared to the distance traveled by hydrogen chloride. See that the hydrogen chloride travels a far less distance than that of ammonia. So why does that happen? Okay, so it has to do with the rate of effusion or the rate of diffusion of the gas molecules. The lighter molecules, which is the ammonia molecules, travel faster, so they will travel a further distance than the heavier molecules of the hydrogen chloride gas. And also we have to take into account the interaction of these molecules with air. So that will also slow the rate of movement. So we asked you to compare the rates of effusion of hydrogen and oxygen at the same temperature and pressure. So we know our equation for comparing rates of effusion. Substance A over substance B, molecular mass of B, square root of molecular mass of B divided by the square root of molecular mass of A. So our two substances are hydrogen and oxygen. So we replace our A and B with hydrogen and oxygen. Now we're going to include our molar masses of oxygen and hydrogen. Oxygen gas has a molar mass of 31.998, so that's about 15.999 times 2. Hydrogen has a molar mass of 2.016 or 1.008 times 2. So now we find the square root of these numbers and divide them, or divide them, then find their square root. And we get a value of 3.984. What is the importance of this number? What does this number tell us? It actually tells us that the rate of diffusion of the hydrogen molecules is about 4 times that of the oxygen molecules. So the hydrogen molecules are actually going to move much faster than that of the oxygen molecules because they are much lighter. So let's look at this example. We're given the rate of diffusion of a particular gas, or we're told the rate of diffusion of a particular gas was measured and found to be 24.0 milliliters per minute. Under the same conditions, the rate of diffusion of pure methane, CH4 gas, is 47.8 milliliters per minute. What is the molar mass of the unknown gas? So we start off by using our equation. We know the rate of diffusion of A over the rate of diffusion of B. Square root of the molecular mass of B divided by the molecular mass of A. So we know the unknown, the rate of the unknown, and we know the rate of the methane gas. So this is our equation now. 47.8 divided by 24.0 is equal to the square root of the unknown molecular mass divided by the square root of the molecular mass of methane, which is 16.0. Now, there's several ways you can go about solving this problem. The way I've chosen to go about this is to start by getting rid of our square root. To get rid of our square root, we square the component. So we square it to get rid of our square root, and whatever we do to one side of the equation, we must do to the opposite side. So now that would give us this value. 3.9667 is equal to the molecular mass of the unknown divided by 16. Now to find the molecular mass of the unknown, we simply transpose to solve for the unknown, which is 3.9667 times 16.0. Now that we have that, we simply multiply, and that gives us the unknown molecular mass of 63.5 grams per mole. So here we have used the Graham's law of diffusion to solve for the unknown molecular mass of a compound. Now, molecular weight at STP. Now, the molecular weight at standard temperature and pressure can be found by using this equation, dRT over P. So where MW is the molecular weight, D is the density in grams per liter, all right, at STP. So the molecular weight can be said to be the density in grams per liter multiplied by 22.4 liters per mole. Because at STP, 1 mole of a gas occupies a volume of 22.4 liters. So if we take the density and multiply by the volume of 1 mole of a gas, then we'll get the molecular weight, or we get the weight in grams per mole, because our liters will cancel. That leaves us with grams, units of grams per mole, which is the units of molecular weight. To calculate density, we simply take the molecular weight and divide it by the volume of 1 mole of a gas at standard temperature and pressure. So here our moles will cancel, leaving us with grams per liter. So at 22 degrees Celsius and the pressure of 755 torr, a gas has a density of 1.14 grams per liter. What is the molecular weight of the gas? So first thing we do is start breaking down your question. What are you given? Identify what you're given. You're given temperature, first thing. And we know we're dealing with a gas law. We're dealing with gases, so the temperature must be in Kelvin. So convert your degrees Celsius to Kelvin by adding 273. Then we're given pressure in torr. But when we're dealing with gas laws, we would prefer to work with gases in pressures of atmosphere, sorry. So you can convert your torrs to atmosphere. We know that in 1 atmosphere we have 760 torr. So that gives us 0.993 atmospheres. So that's our pressure in atmospheres. Then we also have the density of the gas, 1.14 grams per liter. Now we ask to find the molecular weight. So we have these variables and we need to find molecular weight. Molecular weight is dRT over P. Density times our ideal gas constant multiplied by the temperature in Kelvin divided by the pressure. So we substitute our values. We take our density multiplied by our ideal gas constant with units of liters per atmosphere per mole Kelvin, multiply by 295 Kelvin, and divide by our pressure in atmosphere, which is 0.993. When we do that, we'll get an answer of 27.8 grams per mole. So that is the molecular weight of the unknown gas. So here we've seen that we've just taken what we're given, broken it down from the question, converted our temperature from Celsius to Kelvin, converted our torrs to atmospheres. Note, we could have used torrs in the question, except if we use torr, then we'd have to use a different value of R. We'd have to use our value, an ideal gas constant, that's in terms of torrs. Then we have our density. We use our equation, molecular weight is equal to dRT over P. Substitute the values that we have and solve for our unknown. And our unknown in this case was the molecular weight. This question asks, what is the density of oxygen gas at 25 degrees Celsius and 745 torr? So again, temperature. Convert a temperature into Kelvin, from Celsius to Kelvin. We're given the pressure in torr. We can convert the pressure in torr to pressure in atmospheres. That's 0.980 atmospheres. We're given the molecular weight because we know oxygen gas, which would be approximately 32.0 grams per mole, but we don't have the density. So we use our same equation. We'll have to transpose our equations to solve for the density. So it's molecular weight times the pressure divided by RT. Once we've done that, we're going to substitute the values we have. We have our temperature. We know what R is, the ideal gas constant. We know what the pressure is, and we know what the molecular weight is. So we put these values into our equation. And then we go ahead and solve for the unknown, which is our density. And we get a value of 1.28 grams per liter. So all we're doing is identifying what you're given. Once you know what you're given, look and see what equation you're going to use. In this case, we want density. So we know that density of a gas, we use that equation. Molecular weight is equal to dRT over P. And we want density, so we need to transpose the equation to solve for density. We're given molecular weight, we're given the pressure, we know the ideal gas constant, and we know the temperature in Kelvin. So substitute these values into the equation and solve for the unknown, which is your density. Alright, so we're given this question and we're told the explosive decomposition of nitroglycerin may be formulated as, and we're given the equation. What pressure would result from the detonation of 5.0 grams of nitroglycerin in a sealed 1.0 container, assuming the resulting gases attain a temperature of 2,457 degrees Celsius? So let's break down the question. We're given the volume of the container. We're given the temperature in degrees Celsius, which we've converted to temperature in Kelvin. We're not given the pressure because we want to find that. We're not given the number of moles. Ultimately, we want to find the number of pressure. So that means we have to find the number of moles first. So what equation can we use to find that number of moles? So think of the equation PV is equal to nRT. So we can use that equation to solve for that pressure. But first, we must know the number of moles. So that means we're going to have to do stoichiometry with these gas problem. So we start with grams of nitroglycerin. and we want to find moles of gas. We're given 5 grams of nitroglycerin. Now we need to find how many moles of nitroglycerin we have in 5 grams. In 1 mole of nitroglycerin, we have 227.0 grams of nitroglycerin. Then we go to our equation, use our stoichiometric ratio. Since we're talking about the resultant gases, we're not talking about just one gas in particular. So I'm not talking about carbon dioxide, water or water vapor, nitrogen, and oxygen by themselves. We're talking about a combined number of moles of gases. So we add our coefficients for our gases. So we have 12 plus the 10. So 12 CO2 plus 10 water, that gives us 22. Plus the 6 nitrogen, that gives us 28. Plus the 1 oxygen. So we have 29 moles of gas to 4 moles of nitroglycerin. So now we can go ahead and solve for our moles of gas. So we multiply the 5.0 by 29, divide that by 227, and then again divide by 4. So that gives us 0.1597 moles of gas. So now we have the moles of gas, we can go ahead and solve for the pressure. We know V already, R is a constant, and we know the temperature. So we rearrange that equation, the Pövner equation, to solve for P. So that means P is equal to nRT over V. So we substitute our known values into the equation. Once we've substituted our known values into the equation, we can solve for P, and that gives us 36 atmospheres. So that means the pressure that results from the detonation of 5.0 grams of the nitroglycerin in that 1.00 liter container, assuming that the gases reach a temperature of 2,457 degrees Celsius, it's going to be 36 atmosphere. One of the waste products of operation of an ordinary internal combustion engine is nitric oxide, resulting from oxidation of some of the nitrogen in the air. Nitric oxide emitted from the exhaust engine is photochemically converted to nitrogen dioxide, and we're given the equation. We're asked what mass of nitrogen dioxide would result from the photochemical oxidation of 65 liters of nitric oxide measured at 27 degrees Celsius and 700 torr. So let's analyze the question. We're given the pressure in torrs, which we can convert to atmosphere. We're given the volume. We don't know how many moles of the gas we have. And we're also given temperature in Celsius. So we can convert our Celsius to Kelvin. So that means we can use the equation PV is equal to nRT to find the number of moles. So we use our ideal gas equation. So we can solve for the number of moles, PV divided by RT, substitute the known values into the equation, and once we've done that, we solve for the number of moles of nitric oxide. So now that we have moles of nitric oxide, we need to find grams of nitrogen dioxide that can be produced. So we're going from moles of nitric oxide to grams of nitrogen dioxide. We have to do stoichiometry. So we start with moles of our nitric oxide and we want to get to grams of nitrogen dioxide. We calculated 2.431 moles of nitrogen dioxide. Then we want to convert moles of nitric oxide, We have 2.431 moles of nitric oxide, which we need to convert to moles of nitrogen dioxide. We look at the mole ratio of nitrogen dioxide to that of nitric oxide. It's a 2 to 2 or a 1 to 1 mole ratio. So we have 2 moles of nitrogen dioxide and 2 moles, moles, MOL, 2 moles of nitric oxide. We want to go from moles of the nitrogen dioxide now to grams of nitrogen dioxide. There are 46 grams of nitrogen dioxide in 1 mole of nitrogen dioxide. And we go ahead and solve this problem, which would simply be 2.431 times 46. That gives us approximately 110 grams because we've rounded off to our 2 significant figures. So here we've seen how to use the gas law equations and solve stoichiometry problems involving the gas law problem. Gas law, sorry. We've also talked about the rate of effusion and the rate of diffusion using Graham's law, calculating the molecular weight of an unknown gas, whether we use Graham's law or we use the molecular weight is dRT over P equation. So that takes us to the end of this one. Until the next time, I'm out. Blessings.